Okay, so today's lesson is to focus a little bit more on those special angles. And so what we're going to do is recall what we actually know about these angles from geometry. And remember, they're special, it's kind of arbitrary. They're things that came up or do come up often in our number system or the way we build things, which is why we choose to remember these ones specifically. So if you guys remember from geometry, in a 30, 60, 90, there is the shortest side of the triangle. Then there's kind of the other leg of the triangle, which would be the middle length side. And then there's the hypotenuse, which is the longest side of the triangle. And what you should have found in geometry after doing a lot of work with these patterns is that if you knew the short leg measurement, I'm going to call it n, that the hypotenuse would be double that measurement, and the middle length leg would be that measurement times the square root of 3. For a 45, 45, 90, both the legs are equal, and then you have your hypotenuse. So in this situation, if you know one leg, then you automatically know the other. And the hypotenuse, the pattern that we found, is that it's equal to the length of the leg times the square root of 2. So we have a chart down here that has like one piece of given information and some others missing, kind of like solving the special right triangle. And we're just going to go through a couple of examples. So for example, let's look at this first one. Okay. If someone told me the middle length leg was 5 rad 3, then that would mean I have a 30, 60, 90, and I know that this is 5 rad 3 in a triangle where I know the pattern is this number times rad 3, and double that number. So what they're telling me is that the number times rad 3 turns out to be 5 times rad 3. So the number times rad 3 actually equals 5 times rad 3. If I solve that kind of little mini equation, it tells me the number I'm looking for to fulfill my patterns is 5, which means the short leg is 5, and the hypotenuse is 2 times 5, which is 10. So the numbers filled into this pattern here would be 5 and 10. Okay. Then let's say I look at this problem here where they tell me the hypotenuse is 8. Okay. I'd be in a similar situation, so I'm going to change. It's still the same kind of triangle, but this time they're telling me that the hypotenuse, the longest leg of the triangle across from the 90-degree angle, is 8. So when I think about my pattern again and how it fits these triangles, what they're giving me is that double that number that I want to know is equal to 8. So double some number equals 8. If I solve that kind of mini equation or puzzle, I get that the number is 4. So that tells me the short leg is 4 and the other leg is 4 times rad 3. Okay. All right, so now let's look at if the hypotenuse given to you was 1. So this last problem in the chart. So we're going to redo the same information that we just did, but say that we were given a hypotenuse of 1. And we're going to see how that works out. So right now we would know double some number equals 1 instead of 8 this time. And that means the number I'm looking for is 1/2. Okay. So that means this is 1/2, and this is 1/2 times rad 3. And that would equal rad 3 over 2. So this would be 1/2, and this would be rad 3 over 2. Okay. And then we're going to look at some of your 45, 45, 90 ones to establish that we remember how to use these patterns correctly. So let's look first at the first one. So any leg they give you, you know that the other leg is the same, because remember now we're talking about 45, 45, 90s. So if one leg is 4, then the other is 4. And then according to the pattern, this one would be 4 rad 2. Okay. Let's look at this middle one. If they gave us the hypotenuse was 13 rad 2, which is still a pretty nice problem. remember that they're telling you that this portion of your pattern, that n rad 2, is equal to 13 rad 2. So you kind of know this little equation, and we can solve it by dividing by rad 2 to see the value of n, and that would give us 13. So that would mean these are 13. So in this problem, these would be equal to 13. And then we're going to look at this last one right here. So in the last problem, they're giving us a hypotenuse of 1. And I'm going to label that pattern around my triangle again. So I know that there's supposed to be 2 lengths of the legs that are equal and that the hypotenuse should equal 1. So if this is equal to 1, then I get that n is equal to 1 over rad 2, and we usually don't leave a radical unsimplified in the denominator like that. And so this gives us rad 2 over 2. Okay, and so that would be rad 2 over 2, and so would this. So these lengths of the triangle would be rad 2 over 2. Okay. So this was a good little review of using patterns of special right triangles. But really for us, these are the key questions. How does this relate to our unit circle, and how can we figure, what can we figure out from this information? So we're going to go back to the unit circle on the previous page, and we're going to see how it relates. So here's a picture of your unit circle, and right now I'm going to kind of isolate and zoom in on this position of this 30-degree angle right here. Now remember, if I draw the initial side of the angle and the terminal side, this is the portion in between them that I'm measuring as 30 degrees. If I connect this back down to the x-axis, I've just created in this area right here a right triangle with a 30-degree angle, which means this is a 30, 60, 90 triangle. For this triangle, the short side would be over here, the other length side would be over here, and the hypotenuse is along here. But this isn't just a circle, this is the unit circle, and remember the definition of the unit circle was that we knew the hypotenuse is equal to 1. Okay? So I'm going to have you look back at the page that we just filled in. We did this right here when there was a 30, 60, 90 triangle and the hypotenuse was equal to 1. You knew that the short leg was 1/2 and the middle length leg was rad 3 over 2. So, sorry, wrong direction. In my triangle right here, if I know the hypotenuse is 1, I know that the short leg is 1/2 and that the other leg is rad 3 over 2. So why does this matter in your circle? It matters because this position that we're naming right here can be named 2 different ways. Actually, you see multiple blanks, but one way is by the angle, the 30-degree marker, which you've put right here. Okay. We'll also name the angle in radians, but we'll learn that after spring break. The other way to get here is with x and y coordinates. Like, what are the coordinates to land at that point on the x and y coordinate plane? And what you have right here, this rad 3 over 2 tells me you have to go over to the right rad 3 over 2, and then you have to go up 1/2 to get to this point. So this point might be marking 30 degrees on the unit circle. However, it's also marking rad 3 over 2, comma, 1/2, those ordered pairs. Okay? So that idea can then help us figure out other ideas as well. Let's look at the 60-degree angle. So here's my 60-degree angle. If I connect that back to the x-axis and make a right triangle, here's now the right triangle that I'm looking at with a 60-degree angle right here. So that's a right triangle with 60 degrees. 30 would be here. And again, you know the hypotenuse is 1, which means this is still a 30, 60, 90, and you know that the short side is 1/2, the longer side is rad 3 over 2, So to get to this point right here, you either name it as a position of 60 degrees around the circle, or a position that you've traveled 1/2 units to the right and rad 3/2 units up to land at this point. Okay. I'm going to erase the extra triangles and stuff off of my circle now, and I'll relabel everything. It's just getting a little messy for you guys to see the work that we're doing. So let's take this off. All right. And then I'm just going to put back in the labels. So there's my 60-degree angle. I'm going to label my 30-degree angle. And I am color coding it on purpose. And my 45-degree angle. It's 0. Okay. So these coordinates look similar because they came from the same triangle, just kind of like turned a different direction so that a different side was considered the short side. And that's why we see those numbers there. Now we're going to look at the 45, 45, 90 triangle, which means we're specifically going to look at this 45-degree angle. And if we drew a triangle here, this is a 45, 45, 90. And again, we know the hypotenuse is 1. I'm going to refer back to that page that we were working on. In a 45, 45, 90, if we knew that the hypotenuse was 1, we use rad 2/2 and rad 2/2 as the two side lengths of the triangle. That means in this position, I know this side length of the triangle along the x-axis is rad 2/2, and I know this length of the triangle that's going vertically is rad 2/2, which means to get to this point on my circle, I could describe that name as 45 degrees if I speak about it in terms of angles. If I talk about it in terms of coordinates, it's rad 2/2, comma rad 2/2 to get to that position. Okay. So this is how our triangles are helping us. And I'm going to just erase this work again so we can use this circle differently in order to see these different patterns that are on here. So then you might be a little concerned, like, how are we ever going to get the other angles? Because you wouldn't draw a 120-degree angle in a right triangle. You'd have too many degrees. But instead, I want you to just think about reflecting these positions over. So if I think about what I have here with this 30-degree position, we talked about this little triangle that exists here. Notice where I can reflect that triangle. That same triangle, if I reflect it over the y-axis, would end up over here. Okay? Meaning, to get to these coordinates right here, I have the same horizontal distance that I had on the other side, which means rad 3/2 as an x. And I have the same vertical distance, which means 1/2 as a y. But how do I land over here instead of landing over here in the first quadrant is that I have a negative x value instead of a positive x value. Okay. And then you can see the reflection again. If I reflected that triangle now over the y or over the x-axis, I would land at this position down here below 180. So this is 30 degrees below 180. Again, this has the same horizontal distance as the point above it and the same vertical distance. So again, the distance we're traveling horizontally is rad 3/2 and vertically is 1/2. But what makes us land down here in the third quadrant instead of landing up here in the second quadrant is that not only do we have a negative x, but we also have a negative y coordinate. And then you could do a reflection yet again, or a reflection from your original triangle over to this side, which puts you at this 330-degree position, which would have, again, the same x distance and the same y distance. So it would be rad 3/2 and 1/2. But how do we land in the fourth quadrant? Instead of the first, second, or third, we have a positive x, but we have a negative y. So there's kind of all the symmetry that you see happening there with all these reflections. So that's kind of where we're at. All right, we are then going to look at what if we expand this idea and we reflect the other positions as well? So what that means is everything that I coded here in blue had the same coordinates as that 30-degree angle because they would be those coordinates flipped, okay? And I'm going to keep just the position highlighted. So 30, that's a 30, this is a 30, and this is a 30. So I would refer to those all as kind of 30-degree angles in a way because of how they're drawn. Now, if I look at the 60-degree angles, notice that those ones are 60 degrees away from the x-axis, 60 degrees away from the x-axis down here, 60 degrees away from the x-axis up here, 60 degrees away from the x-axis down here. That means all of those angles are going to have the same coordinates, but to land in the different quadrants. So again, to land in the second quadrant, I would need a negative x coordinate and a positive y. To land in the third quadrant, I would need a negative x and a negative y. To land in the fourth quadrant, I would need a positive x but a negative y. Then what I'm going to do is expand this idea one more time to the 45 degree angles. So we see the 45 right here. There's another one right here, another one right here, and another one right here, which means at those positions, we could draw a triangle that's just a reflection of those 45-degree coordinates, which notice are both the numbers rad 2 over 2. If I reflect them to the other side, again, to land in the second quadrant, that's a negative x and a positive y. If I reflect that to the third quadrant, that's a negative x and a negative y. And if I reflect over to the fourth quadrant, that's a positive x with a negative y. And then lastly, we need to label the points that aren't really going to make triangles, but here at our axes. But remember, again, this is a unit circle, okay? So when I make this point right here, I should know that the y coordinate is 0. And in this case, the x coordinate is going to be 1 because the radius of the circle is 1. Up here at 90 degrees, the x coordinate is 0, but the y coordinate is 1. At 180 degrees, the x is 1, but negative 1 to land me on this other side of the circle with a y coordinate of 0. And at 270 degrees, an x coordinate of 0 and a y coordinate of negative 1. So those special right triangles kind of help us establish a position in two different ways. Now we can tell someone how to get to a point on this unit circle in two ways. The position can be described with coordinates or it can be described with angles.